10.4, dividing radical expressions. So this first one, we want to simplify. So you have to ask yourself, looking at the fraction on the inside, is there anything that can first be just simplified within the fraction? And if we notice, we can actually cancel the 2 out of the 32, right? So let's go ahead and do that. So the 2 will cancel with the 32, leaving a 16. So that leaves us with the 4th root of 16a to the power of 4 over b to the power of 4c to the power of 8. Now nothing can be simplified on the inside, so in order to simplify this, we can turn this into 2 separate radical expressions. Remember, the division rule or the quotient rule basically states if you have a quotient or basically a fraction inside of a radical, you can split it into 2 of them. So we can make this the 4th root of 16a to the power of 4 divided by the 4th root of b to the power of 4, c to the power of 8. Now let's go ahead and simplify each one individually. So in the numerator, the 4th root of 16 is 2, and remember, this number tells us, this index tells us how many per group. We're looking for groups of 4. We have 4a, so we can pull out an a. Nothing remains on the inside. Over, same thing here. We'll have a b, and we have 8 c's. We can pull out 2 groups of 4. Now this one, notice we are given the 2 expressions separately. We have the cube root of 96a to the power of 4b squared divided by the cube root of 12a squared b. But if you notice on the inside, the 96 and the 12 can actually be simplified. We have factors of a and b on top and bottom, so they can be simplified. But in order for us to simplify this, we have to write this as one fraction within a radical. So we'll go ahead and combine this to the cube root of, so don't be lazy. Oops, where did it go? 96 a to the 4 b squared over 12 a squared b. Okay, so what does that simplify to? 12 goes into 96 8 times, so we have the cube root of 8. A to the 4 divided by a squared is a squared, and b squared divided by b is b. And now we ask ourselves, can anything be taken out? Do we have any perfect cubes? Well, 8 is a perfect cube of 2, and nothing else is, right? We only have 2 factors of a, 1 factor of b, so we can't pull out groups of 3. So we're left with 2 cube root of a squared b. Now this one tells us to rationalize the denominator. So this is very important. So we've always talked about what it means to have a simplified fraction, right? A simplified fraction, for instance, I'm going to write here on the side, you would never leave a final answer as 6 over 8. You always reduce your fraction. So this would be reduced to 3 over 4 by basically dividing out any common factors in the numerator and denominator. Well, another rule that we have for a simplified fraction is you cannot have a radical expression left in the denominator. You have to basically get rid of the radical. So that's what we mean by rationalizing the denominator. So here, the first thing we're going to ask ourselves is, can we simplify the fraction? And we cannot, nothing cancels. So now we'll go ahead and separate this out into 2 separate radical expressions. So the cube root of 5 divided by the cube root of ab squared. So now what I want to do is I want to basically go ahead and multiply another expression in here so that I can actually achieve the number of factors needed to basically pull these factors out. So we need to focus on our index. The index is 3, which means the only way I can pull a factor out is if there are groups of 3, right? So let's look at the a. How many factors of a do we have? We have 1, because a is raised to the power of 1. Well, if we wanted 3, how many more do we need? We need 2 more. I can't just simply go and add in 2 more. Remember, exponent rules say if you're multiplying two expressions with the same base, you can add the exponents together. So that means I would need to multiply an a squared into this so that I can take the a squared times the a and be left with a cubed. But how do I multiply inside a radical? Well, from section 10.3, we learned the only way two radical expressions can be multiplied together is if the index or the indices are the same. So the only way that I can multiply in here is if I multiply by a cube root. So I'm going to do that. I'm going to multiply by the cube root of, so this cube root allows us to multiply with this one. I had an a, one a, I need two more, so I will multiply by a squared. Now let's look at the b squared. That means I have two factors of b, but I need three of them. So how many more do I need? I need one more. Now we go back to our basic rule with fractions. You always want to maintain your balance within a fraction. So if you multiply either the numerator or denominator by an expression in a fraction, you must do the exact same to the other side to maintain the balance. So if I'm going to multiply the denominator by the cube root of a squared b, I have to do the same to the top. So I will go ahead and multiply the same expression to the numerator, cube root of a squared b. So essentially what I'm doing is if you look, if you multiply to the numerator and denominator, well, this really is equal to 1. Right? You have the same expression on top and bottom, it cancels to 1. So when you multiply by 1, you don't actually make a change in value, you just change the way it looks. So now let's go ahead and multiply across. So here we can multiply here the radicands together because they're both cube roots. So we have the cube root of 5a squared b over here, cube root. So cube root of a times a squared is a cubed. B squared times b is b cubed, and the whole purpose of doing this is so we can get rid of the radicals, and here we can see that we can get rid of the radical. I have a perfect group of 3 a's, a perfect group of 3 b's. So this simplifies to the cube root of 5a squared b over ab. Nothing remains, and our radical is gone. And you ask yourself if you can simplify, but we cannot. Even though we have a's and b's in the numerator, they are inside the radical. These are not inside. So that would be our final expression.